Hi guys, it is time for our review session for the final exam. This is going to be split into 4 parts, and the first part we will talk about one-dimensional kinematics, frames of reference, acceleration and velocity, the kinematics equations, free fall, and motion graphs. First of all, frames of reference. A frame of reference is a framework that we use for making observations and measurements. For our time, if our time is 3 seconds, 3 seconds from when? Well, typically it's 3 seconds from when you started the clock. But notice we don't say, we don't plug into a problem 3 o'clock or 7:30. Our frame of reference is when we have a stopwatch from when that stopwatch was, when we turned it on, from 0. For motion, if we're talking about velocity or position, we usually use the Earth for our frame of reference. And so if you're moving 3 meters per second, it's usually relative to the stationary ground. In a problem, we may or may not explicitly tell what the frame of reference is. Sometimes it will be a point, with respect to the people on the shore, how fast was the boat moving, that kind of thing. But if it's not mentioned, it's the Earth. So if you're walking from the back of a ship to the front, what would you use for your frame of reference? So if you were on a ship and you were walking from here to a point here and you wanted to tell someone how fast you were moving, would you tell them how fast you were moving relative to the boat, which is stationary relative to you? Or would you tell them how fast you were moving to this guy that's over here on the shore watching the boat go by? Because if you're moving on top of the boat's motion, your velocity relative to this guy is different than your velocity relative to the boat. So you're probably going to use your boat for the frame of reference as you're walking on the boat. So if you're on a train and you move from the back of the train to the front with a speed of 2 meters per second, and the train is moving at 40 meters per second, what's your speed relative to the train? Well, relative to the train, you're moving 2 meters per second. But relative to the Earth, so if the train's here and you're walking from the back of the train to the front, relative to a person who's out here watching the train go by, the train itself is moving 40 meters per second. You're moving 2 meters per second inside the train, and so this person would see you move with a speed of 42 meters per second. So what if you were walking to the rear of the train? Well, if you were walking to the rear of the train, your speed would actually be, if you're moving in this direction, your speed would be a minus 2 meters per second. And so now the person would see you moving to the right with a speed of 38 meters per second. One-dimensional kinematics. Remember, velocity is a change in position over time. Displacement is our final position minus our initial position. That is how far you are from where you started. Remember, distance is the total distance you travel. So if you went around this square, your distance would be A plus B plus C plus D. But if you end up back where you started, your displacement would be 0. Acceleration is a change in velocity in time. This equation, expressed slightly different, gives our first kinematics equation. Change in velocity, anytime we have a delta anything, delta x is final minus initial position, and a delta v would be a final velocity minus an initial velocity. And if acceleration is final velocity minus initial velocity over time, I can multiply both sides by t, move my initial velocity over, and I get this, the very first of my kinematics equations. If your velocity and your acceleration are in the same direction, then you speed up. Sorry, that's kind of messy. If your velocity and your acceleration are in opposite directions, then you slow down. Now that we've had forces, you know that the direction of the acceleration and force are always the same. And so if you're in a car and you're going this way, your velocity is in that direction, but there's a force acting on your car in that direction, it's going to slow your car down. On the other hand, a force acting in this direction will speed your car up. And acceleration and force are in the same direction. If an object changes speed from 10 meters per second, that's our initial velocity, to 5 meters per second, that's our final velocity, in 2 seconds, find the acceleration. So acceleration is our change in velocity over time, and that's final minus initial, so that's 5 meters per second minus 10 meters per second over 2 seconds. 5 minus 10 is -5. So the acceleration is negative 2.5 meters per second squared. If an object has a velocity of 4 meters per second and accelerates at 2 meters per second squared for 3 seconds, what's its final velocity? Final velocity is initial velocity plus acceleration times time. And if the initial velocity was 4 meters per second and the acceleration is 2 meters per second squared for 3 seconds, so 3, that is a 6 meters per second we get there, plus 4 meters per second. That means our final velocity would be 10 meters per second. The kinematics equations, we already had this one. That is really the definition of acceleration. Vf squared equals vi squared plus 2ad. D equals 1/2 vi plus vft. And d equals vit plus 1/2 at squared. This is displacement. This is not distance, but this is that's actually our final position minus our initial position. So that's displacement, as is this. I want you to look at this value right here. That is just average velocity. So that equation is d equals the average velocity times time. Now, that's not an instantaneous velocity, that's an average velocity. This equation we don't use a whole lot, but these others we use a whole lot. We are not going to address free fall separately, really, than other kinematics problems in this review. The free fall is exactly like the other problems, except you already know the acceleration. Acceleration is not a variable in a free fall problem. The acceleration is negative 9.8 meters per second squared. In a free fall problem, the only acceleration is in the y direction. There is no x acceleration. So in a free fall problem, the x velocity is constant. But that's just in free fall. Okay. Notice in these kinematics equations there are 4 variables. You will be given 3 and asked to solve for the 4th. That actually was a test question on the test on this unit. How many variables are there in all the kinematics equations? And it's 4. You may be accustomed to using different variables than this. You may be used to like this being a v squared and this being a v0 squared plus 2ad. Some books even use s instead of d for distance, but these are the 4 basic kinematics equations. So let's work some example problems. An object starts at rest, so that's an initial velocity of 0, and moves to the right for 3 seconds, that's a time, with an acceleration of 4 meters per second squared. How fast is it moving? So Vf equals Vi plus At. And how do I know to use that? I look back at my equations and I find an equation that has what I'm looking for and the variables I'm given. And this is the equation that fit the bill. And so that's the initial velocity is 0. Acceleration is 4 meters per second squared. And it did that for 3 seconds. So that tells me that my final velocity is 12 meters per second. Okay. A free fall problem that is similar to that, an object falls for 3 seconds. So we're only given time. If it doesn't say anything differently, it falls from rest. And so our initial velocity is 0. And its free fall, so acceleration is negative 9.8 meters per second squared. So we're given all the same stuff, really. So we'll use the same equation. Vf equals Vi plus Gt. And so the initial velocity is 0, and the acceleration is negative 9.8 meters per second squared, and the time is 3 seconds. And if I estimate in my head, that's going to be very close to negative 30. And usually when I'm working problems, I use 10 for G, but since we're doing a class and y'all don't, 29.4. Negative 29.4 meters per second. Our second example, an object is moving with a velocity of 5 meters per second with an acceleration of negative 2 meters per second squared. How long will it take to reach a velocity of negative 10 meters per second? So I have Vi, Vf, A, and T. That reminds me of this equation again. And if I want to solve for t, I'm going to move the vi to the other side and divide everything by acceleration. So that says vf minus vi divided by acceleration equals time. So the final velocity is negative 10 meters per second minus the initial velocity is 5 meters per second divided by the acceleration, which is negative 2 meters per second squared. Negative 10 minus 5 is a negative 15 over a negative 2, which is a positive 7.5 seconds. Just FYI, if you ever solve for time and it comes out negative, you've made a mistake. Time is positive. A similar free fall problem, an object is thrown upward with a velocity, this is a positive because it's moving upward, 50 meters per second. How long will it take to reach a velocity of negative 60? And remember, acceleration is g is negative 9.8 meters per second squared. So using the same equation, I'm going to go ahead and use this version that we've already rearranged. So time is our final velocity, negative 60 meters per second, minus our initial velocity, 50 meters per second, divided by acceleration, negative 9.8 meters per second squared. So that's negative 110 divided by negative 9.8 meters per second squared. This is meters per second. Now, again, if this were 10, that would come out to be 11 seconds. And honestly, if you're taking a multiple choice test, use 10, do it in your head, and then get the closest answer. If 110 divided by 9.8 is 11.2, and you are not going to have both of these answers there and have one of them be wrong. And so I would use the 10, do it in my head, get 11, see that 11.2 is close, and choose 11.2. An object has an initial velocity of 2 meters per second, accelerates at 4 meters per second squared for 3 seconds. How far will it travel? So we're looking for a d. So we have two options. Okay, when I see v's and d's, I think vf squared equals vi squared plus 2ad, but we don't have a final velocity, and we're not looking for it. So we're looking for a distance, we have an acceleration, and we know an initial velocity and a time. So how about d equals initial velocity times time plus 1/2 at squared. All right, so our initial velocity is 2 meters per second times our time, which is 3 seconds, plus 1/2 times our acceleration, which is 4 meters per second squared, times our time squared, which is 3 squared. So 2 times 3 is 6. 3 squared is 9, times 4 is 36. Half of 36 is 18, and 18 and 6 is 24 meters. Another example, an object has an initial velocity of 2 meters per second and accelerates at 4 meters per second squared for a distance of 10 meters. What's the final velocity? Okay, now I am going to use this equation. So vf squared equals vi squared. I'm not going to rewrite it here because it's right there. Vi squared, so 2 meters per second quantity squared plus 2 times the acceleration times the distance, meters. So 10 times 4 is 40, times 2 is 80, plus 2 squared is 4, equals vf squared. So vf squared is 84. And so 84, and hit the square root button on my calculator, 9.2 about meters per second. Okay, don't forget that last step. One of the wrong answers to the problem will be 84, because they want to know if you're going to remember that when you add these two things, you don't get the answer, you get the square of the answer. So be really careful about that. Sometimes you'll have a two-step problem. In this case, given the initial velocity of 3 meters per second and the final velocity of 15 and a time of 4 seconds, find the distance traveled. Well, I don't have an equation that will let me find distance from those, but I can find acceleration, which is final velocity minus initial velocity over time. So 15 minus 3 over 4. 15 minus 3 is 12. 12 over 4 is 3 meters per second squared. And now I have an initial velocity, a final velocity, a time, and an acceleration, and I can find a distance. I can, well, let's use v equals VIT plus 1/2 AT squared. And our initial velocity is 3, our time is 4, plus 1/2 times our acceleration we found is 3, and our time is 4 again, and that gets squared. So 4 squared is 16, and 16 times 3 is 48, and half of 48 is 24, and 3 times 4 is 12, and 12 plus 24 is 36 meters. So our distance equals 36 meters. And a little more free fall. An object falls from a height of 10 meters. How fast is it going at the bottom? Okay, so we have an initial velocity. When I'm not sure where to start, I start writing down what I'm given. I have my initial velocity, I'm looking for a final velocity, I have a distance, and I have an acceleration, because acceleration is negative 9.8 meters per second squared. Okay, so I'm going to use VF squared equals VI squared plus 2AD, putting gravitational acceleration in for my acceleration. So VF squared equals 0, it falls from rest, plus 2 times, I'm going to just say 9.8 here, because otherwise, no, negative 9.8, and our distance is negative 10, because it's going to fall from 0 down to negative 10. So our displacement is a negative value. It's moving in a negative direction. And that's how our sign is going to work out. And so 2 times 9.8, I'm using my calculator here, is VF squared equals 196. And if I take the square root, I get 14 meters per second. And how long did this take? Well, we have acceleration is final velocity minus initial velocity over time. And so time is final velocity minus initial velocity over acceleration. Our final velocity is actually, it came out because of the square thing, everything comes out positive. Velocity is actually plus or minus 14, and in this case it was moving down, so it was minus. So our final velocity is negative 14, our initial velocity was 0, and our acceleration is negative 9.8 meters per second squared. So 14 divided by 9.8 is 1.4, about 1.4 seconds. Okay, we're running a little bit long here. This is probably the longest of the 4 reviews. We still have to talk about motion graphs, and I'll whiz through it as quickly as I can. Sorry, a little bit of this down here is getting cut off, but I can't move it at this point. Or maybe I can. Can I shift that? Let's see if that worked. Okay, 3 different motion graphs. If it's a displacement versus time graph, you've got meters on the y-axis and time on the x-axis. All you need to know is that the slope is the velocity. So in this graph, I can tell that the velocity is constant and positive there. Here, I can tell that the velocity is 0 because the position's not changing and it's flat, and that's a 0 slope. Here, all the way down, I can tell that the velocity is negative because it's a negative slope. And so if I find the slope of that line, I'll know the velocity. And here we're back to having a positive velocity because the slope is positive. Velocity is the slope in a displacement versus time graph. If it's a velocity versus time graph, you have 2 things to know. The slope is now acceleration. So here I know that this object is speeding up because the acceleration is positive. Here, the acceleration is 0, so the velocity is constant. The velocity is not 0. The velocity is not changing. Actually, the velocity is 60 right here, that whole little path. So the velocity is not 0, it's constant. And here I know that the acceleration is negative. So it slows down all the way here. Here the velocity is 0, because that's the 0 point on the graph. But now, even with this negative acceleration, it's speeding up. So it slowed when it had a positive velocity and a negative acceleration, but now it has a negative velocity and a negative acceleration, so it's speeding up. And here it stops speeding up and starts slowing down again with a positive acceleration because it has a negative velocity and a positive acceleration. And it only has a 0 velocity when it crosses that axis. Acceleration versus time, the only thing you have to know, the second thing up here, area under the curve, is displacement. When we talk about area under the curve, we're talking about the area between your graph and the axis. So this area up here represents a positive displacement, and this area down here represents a negative displacement. And you break it up into areas that you know how to find. Like I would probably break this into that triangle and that little rectangle in the middle and this triangle. The area of a triangle is 1/2 base times height. The area of a rectangle is base times height. Find those areas, add them together, and you'll have the area under the curve there. And the same thing here. It's just a triangle, and there's my base and there's my height. So I could find the area of that triangle. This is negative displacement if it's below the axis, and then a positive displacement above. And slope is not useful in an acceleration versus time graph. Only the area under the curve is, and the area under the curve, this area in here, is the change in velocity. Not the velocity, but how much the velocity changed while it was accelerating. And I think that might be, yeah, I'm sorry, those were slides that I meant to delete because I put everything on this nice slide. And that is the end of part 1 of our exam review.